Welcome to the Explainer. Today, we're going to talk about the fascinating and maybe a little weird cousins of sine and cosine, the hyperbolic functions. They might sound super obscure, but you're about to see they are hiding in plain sight literally all around us.
Okay, so let's start with something we all know, right? The good old unit circle. Its equation is simple. X squared plus y squared equals 1. And any point on that circle, its coordinates are just cosine of x and sine of x. We got this.
But what if we did something a little crazy? What if we just reached in and flipped that plus sign to a minus? Now we've got x squared minus y squared equals 1. That is not a circle anymore. It's a totally different beast called a hyperbola. So, if sine and cosine have the circle covered, what functions take care of this shape?
And that, my friends, brings us to the main event, the hyperbolic functions. Yeah, think of them as Trigg's weird cousins. They are the answer to the question we just asked.
The two big stars of this show are hyperbolic cosine, which we call cosh of x, and hyperbolic sine, or sinh of x. Now, here's the twist. Unlike their cousins, their real identity, their DNA, is all about the exponential number e. Cosh of x is just the average of e to the x and e to the negative x.
What's so cool is you can actually see what that formula is doing. Imagine you draw the curve of 1/2 e to the x, that classic swoosh upwards. Then you draw its mirror image, 1/2 e to the negative x. And then for every single point, you just add their heights together.
And what you get when you add them up is this really perfect symmetrical U shape. Now, you might look at that and think, hey, that's a parabola. But it's not. It's a different special curve called a catenary. And that right there is the graph of cosh of x. Now, sin of x is almost the exact same idea, but with one tiny, crucial difference. Instead of adding those two exponential curves, you subtract them. And that creates this awesome S-shaped curve that zooms up from negative infinity, slices right through the origin, and just keeps on going.
So, here's the deal. Because these functions are part of the same family as regular trig, they follow a lot of the same rules, or what we call identities. But there's always a little twist. I'm sure you had this one drilled into your head in school. Sine squared plus cosine squared equals 1. It's the Pythagorean identity. Well, the hyperbolic version is almost the same, but look closely, that plus sign gets flipped to a minus. It's cosh squared minus sinh squared equals 1. See? The twist.
But hey, don't just take my word for it. We can actually prove this thing is true in just a couple of steps. And all we have to do is go back to those definitions using e.
So, first step, we just swap out cosh and sin for what they really are, those expressions with e. I know, it looks a little messy at first, but stick with me because this is where the magic happens. Okay, now we just expand those squared terms. And when we do, look at what pops out. Most of the terms are identical in both expressions, except for that number in the middle. We get a +2 from the cosh part and a -2 from the sinh part. That's the key.
And here's the beautiful part. When you subtract the second thing from the first, all those e to the whatever terms, they just cancel out. Poof, gone. You're left with 2 minus -2, which is just 4. And 4 divided by 4 is 1. And there you have it. The identity works. So cool.
Okay, let's kick it up a notch and talk calculus, because this is an area where, you won't believe it, hyperbolic functions are actually, well, they're kind of nicer to work with than their famous cousins.
Remember with regular trig functions how that pesky negative sign keeps popping in and out when you take derivatives? The derivative of sine is cosine, but the derivative of cosine is negative sine. Ugh! But now, look at the hyperbolic side. The derivative of sin is cosh, and the derivative of cosh, it's just sin. No sign change. It's this perfect, clean, happy little cycle. And that's not just a neat little party trick. That elegant simplicity, getting rid of those alternating signs, is a huge deal. It makes solving all sorts of complicated problems in physics and engineering so much cleaner and way less likely you'll make a silly mistake. But wait, there's more. These functions are hiding one more major surprise. They have a kind of secret identity that connects them to a completely different part of math that you'd never expect. Logarithms.
So, if we look at the inverse functions, the ones that undo what cosh and sinh do, we find something totally wild. You'd think they'd be some new, complicated thing to memorize. But they're not. They're actually just logarithms, wearing a costume.
I mean, just look at this. The inverse hyperbolic cosine of x is literally the natural log of x plus the square root of x squared minus 1.
That deep, hidden connection between hyperbolas, exponentials, and logarithms is honestly one of the most beautiful things in all of math.
Okay, so this is all really cool math theory, but does any of this actually, matter in the real world? Oh yeah, big time. In fact, it's been hanging right in front of your face this whole time.
Hey, remember that U-shaped curve we built way back at the beginning of this? The graph of cosh of x? With that shape, it's called a catenary. And it is the exact perfect curve that any chain or rope or power line makes when it's just hanging under its own weight. It's not a parabola, even though it looks like one. It is the real-world, physical embodiment of the cosh function.
And because of that, cosh of x is a superstar function for architects and engineers. They use it to design everything from suspension bridges to the power lines that bring electricity to your home. This isn't just some mathematical curiosity, it's a blueprint for building the world around us.
This incredible link, from an abstract formula with E in it to the shape of a simple hanging chain, is just a perfect example of math's hidden power. It really makes you stop and wonder, doesn't it? What other amazing secrets about how the universe works are just hiding inside the math we thought we already knew?